Okay, Assalamualaikum and hello to everyone. In this video, I'm going to share with you how to design a PV system based on the amount of energy we want to generate. In our previous class, we already did a design based on maximum power, and you are encouraged to refer to the video available in Microsoft Teams for revision. So now, apart from designing based on maximum power, we can also design based on the amount of energy and based on the budget. So we want to now design based on the amount of energy, and we are going to discuss straight by using an example. So the example is given here. A client is requesting to have 80% of her electricity to be offset by energy produced from PV. A historical record of her monthly consumption from the previous year is as follows. So this is example of the client's consumption. So we have the energy consumption for each month. However, there are 2 months where the data is not available, which is for the month of March and May. And the rest we have. And then we also have other information, which is the average daily peak sun hour, which is 4.5 hours, average maximum ambient temperature 34 degrees C, cable loss 3%, and inverter efficiency 95%. So the question asks us to show the necessary design steps and determine the minimum number of modules required to fulfill the client's request. And the module to be used is this model here, which is the same model that we use to solve for maximum power design. So here are the steps on how to solve. So number 1, calculate the sum of energy from the table. So I am going to do the steps straight away here. So step number 1, we are summing all the energy. Alright. So based on this table, we sum all the available energy for each month, and from my calculation, I get the value as 5,200 kilowatt hour. And you can verify it on your own. And then step 2, we are going to calculate the amount of energy required. Since the client requested that he or she wants to offset 80%, so the percent of offset is 0.8, and then we multiply using this equation here. So 12, which is 12 months in a year, divide by the number of months with data, which is 10. So we have 2 months of missing data. So we divide that, and then we multiply with the sum of energy obtained from the first step, 5,200. So if we have a full year, 12 months data, we have no missing data, then we are also going to have 12 here. So 12 divided by 12 is equal to 1. So actually there's no need for us to calculate if we have all the data for each month. So, but in this case, there are 2 months of missing data, so we need to estimate those months with no data, which is why we have this ratio here. So we calculate, and I get 4992 kilowatt hour. Okay, and then step 3 is the annual PSH. So from the question, the given PSH is daily PSH. So daily PSH is 4.5 hours. So we multiply by 365 days. So we have a PSH annual is equal to 4.5 hours multiplied by 365 days. So we get 1642.5 hours. Okay, and then step 4, we calculate all the derating factors given. Step 4, we calculate the derating factors. Okay, the derating factors refer to elements that can cause losses to the PV system. In this question here, it's given the ambient temperature, the cable loss, and the inverter efficiency. So we need to calculate what is the derating factor due to temperature, derating factor due to cable loss, and derating factor due to inverter efficiency. So all the derating factors we label with the symbol K. So for inverter, K inverter, since the efficiency is 95%, so the derating factor is equal to 0.95, which is 95 divided by 100. Straightforward. For the cable, okay, the cable loss is at 3%. So that means the derating factor, K cable, is equal to 100 minus 3% divided by 100. So you are going to get 0.97. Okay, you don't need to show this calculation because it's too simple. You can straight away plug in this number. Now, the next one, this one you need to show, which is the temperature. What is the temperature derating factor? K-temp. Specifically, we want to know what is the K-temp for power. K-temp PMP. Alright. So you need to go back and refer to the equation K-temp PMP. How do we calculate the derating factor for power? So we have 1 plus negative gamma PMP, sorry, gamma PMP. We don't have negative. Gamma PMP divided by 100 multiplied by T cell or T module minus TSTC. Okay, T module or T cell or T cell. Okay, so first we need to check back what is the value of gamma PMP. So gamma PMP refers to the temperature coefficient of power. So we go back a few slides just to check on the module. So the temperature coefficient of power here is given as negative 0.485% per degree C. Okay, so we are going to use that. And then what about the module temperature? Okay, we also need to consider the module temperature or the cell temperature. So how do we calculate? Given in the question just now, the ambient temperature maximum average maximum ambient temperature is 34. So 34 is the benchmark or the reference point of the ambient temperature, right? So in order to estimate the module temperature, we need to go back to the slides on PV basics. So here is the slide that I'm talking about. If we have NOCT value, then we need to calculate using the NOCT value. And we put the ambient temperature here as 34. If we don't have the NOCT value, then we use the second method, which is 34 plus 25. So here, because if we refer to the slide or refer to the data sheet, there's no NOCT value. We are going to use the second method, plus 25. Okay, but when we replace in this equation later, TSTC, as we recall, is always 25 as well. So basically, we are going to put in the value of 34 degrees in this part here. Okay, because T module is ambient temperature 34 plus 25, and then we minus 25 again. So basically, we are going to put 34 degrees inside here. So now we have all the values we need. So 1, negative 0.485 divided by 100 multiply by 34, and you are going to get the answer as 0.8351. 835. Okay, so we've calculated the derating factors based on the question. So in this question, there's no other derating factors provided. So we only need to calculate these three. So the total losses is K losses equal to K inverter multiply by K cable and multiply by K tank. Okay, be careful. We need to multiply and not add. Multiply, don't add. If you add, then all your answers after this will be wrong. So we have 0.97, sorry, inverter is 0.95, cable is 0.97, and temperature temperature effect is 0.83. 0.8351. And I get the total will be 0.7695, I think. So I rounded up to the second decimal point. Okay, so let's I need to open a new page, I think. Okay, so now we move on to step number 5. So step number 5, we calculate the P array STC using the equation here. So P array STC equals the energy required. So the energy required just now is 4992 kilowatt hour. 4992 kilowatt hour, and then divide by the PSH POA. Okay, POA here stands for plane of array. Basically, we want to calculate the annual peak sun hour. Plane of array, that means the peak sun hour as seen by the module. Okay, so we just put the value we calculated just now, 1642.5. Okay, hours, multiply by the losses, we calculate as 0.77. So here we have the hour and hour cancel out, so the losses don't have a unit. So we do the calculation, and I get the array STC needed is 3.947 kilowatt. Okay, this is the capacity of PV panel or PV array that we require to fulfill the client's request. So for PV systems, for PV systems, there's another term we sometimes use to determine the capacity, to represent the capacity, which is kilowatt peak, but that we reserve for another topic. So 3.947 kilowatt. Now we can calculate step 6 by simply having n min equals to round up the P array STC. So P array STC is 3.947 kilowatt. Divide by the rated power for one module, which is 235. Okay, this is the rated power for one module, and you to 235 just now. So if you calculate, you should get a value of 16.8. And remember, modules, we don't have decimal points. Either we have 16 or 17. So which one? We need to use 17 because 3.947 is the amount of this is the capacity required, and it is equivalent to 16.8. If we use 16 modules, then we have less than the amount of capacity that we want. So we need to choose the nearest one. That's why we use the term round up here. So we round up into 17 modules. So now we have already answered the question. To satisfy the client's requirement, for 80% electricity coming from PV, from solar PV, based on his or her energy requirement, we need to install at least 17 modules for the type of Sharp NU235. So this is how you solve a design question based on energy requirement. Okay, I just want to cover a bit on design based on cost. This one is the most straightforward. We simply divide the budget based on the cost to install 1 kilowatt system. Okay, so now I introduce you to this term here, kilowatt peak, KWP. P here stands for peak. Okay, it's used to describe PV modules because the capacity is the peak value, the maximum that can be reached by the PV system. In actual practical application, the amount of capacity is going to be reduced because of the losses that are already embedded in the system. The losses is surely going to happen. But this one is the representation on the peak value or peak capacity. So for example, if a client has a budget of 50,000 ringgit, how large can his PV system installation be? So we need to know what is the cost per kilowatt peak. And the cost it changes year to year. Okay, so for example, let's say we just put a simple example. If 1 kilowatt peak is equals to RM 5K, then we just simply divide 50K with 5K to come up with the answer. The client can install a system with a capacity of 10 kilowatt peak. So design based on cost is very straightforward. Okay, so that's the end of this topic on design based on energy requirement and design based on cost. Any questions, you can contact me through WhatsApp or through our Microsoft Teams group. Thank you.